to help make wireless communications clear. Sprint is proud to support Nova.
We see an inventor. At Microsoft, your potential inspires us to create software that helps you reach it. Your potential, our passion. Funding for the Elegant Universe is provided by the Alfred P. Sloan Foundation to enhance public understanding of science and technology. And by the National Science Foundation, America's investment in the future. Additional funding is provided by the George D. Smith Fund and the U.S. Department of Energy, fostering science and security. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and Cable Television. Thank you. It's a little-known secret, but for more than half a century, a dark cloud has been looming over modern science. Here's the problem. Our understanding of the universe is based on two separate theories. One is Einstein's general theory of relativity. That's a way of understanding the biggest things in the universe, things like stars and galaxies. But the littlest things in the universe, atoms and subatomic particles, play by an entirely different set of rules, called quantum mechanics. These two sets of rules are each incredibly accurate in their own domain, but whenever we try to combine them to solve some of the deepest mysteries in the universe, disaster strikes. Take the beginning of the universe, the Big Bang. At that instant, a tiny nugget erupted violently. Over the next 14 billion years, the universe expanded and cooled into the stars, galaxies, and planets we see today. But if we run the cosmic film in reverse, everything that's now rushing apart comes back together. So the universe gets smaller, hotter, and denser as we head back to the beginning of time. As we reach the Big Bang, when the universe was both enormously heavy and incredibly tiny, our projector jams. Our two laws of physics, when combined, break down. But what if we could unite quantum mechanics and general relativity and see the cosmic film in its entirety? Well, a new set of ideas called string theory may be able to do that. And if it's right, it would be one of the biggest blockbusters in the history of science. Someday, string theory may be able to explain all of nature, from the tiniest bits of matter to the farthest reaches of the cosmos, using just one single ingredient, tiny, vibrating strands of energy called strings. But why do we have to rewrite the laws of physics to accomplish this? Why does it matter if the two laws that we have are incompatible? Well, you can think of it like this. Imagine you live in a city ruled not by one set of traffic laws, but by two separate sets of laws that conflict with each other. As you can see, it's pretty confusing. You need to find a way to put these two conflicting sets of laws together into an all-encompassing set that makes sense.
We've got the assumption that there is a theory out there, and it's our job. We're sufficiently smart, sufficiently industrious to figure out what it is. We don't have a guarantee. It isn't written in the stars that we're going to succeed. But in the end, we hope we will have a single theory that governs everything.
But before we can find that theory, we need to take a fantastic journey to see why the two sets of laws we have conflict with each other. And the first stop on this strange trip is the realm of very large objects. To describe the universe on large scales, we use one set of laws, Einstein's general theory of relativity, and that's a theory of how gravity works. General relativity pictures space as sort of like a trampoline, a smooth fabric that heavy objects like stars and planets can warp and stretch. Now, according to the theory, these warps and curves create what we feel as gravity. That is, the gravitational pull that keeps the Earth in orbit around the Sun is really nothing more than our planet following the curves and contours that the Sun creates in the spatial fabric. But the smooth, gently curving image of space predicted by the laws of general relativity is not the whole story. To understand the universe on extremely small scales, we have to use our other set of laws, quantum mechanics. And as we'll see, quantum mechanics paints a picture of space so drastically different from general relativity that you think they were describing two completely separate universes. To see the conflict between general relativity and quantum mechanics, we need to shrink way, way, way down in size. And as we leave the world of large objects behind and approach the microscopic realm, the familiar picture of space in which everything behaves predictably begins to be replaced by a world with a structure that is far less certain. And if we keep shrinking, getting billions and billions of times smaller than even the tiniest bits of matter, atoms and tiny particles inside of them, the laws of the very small, quantum mechanics, say that the fabric of space becomes bumpy and chaotic. Eventually, we reach a world so turbulent that it defies common sense. so twisted and distorted that the conventional ideas of left and right, up and down, even before and after, break down. There's no way to tell for certain that I'm here, or here, or both places at once. Or maybe I arrived here before I arrived here. In the quantum world, you just can't pin everything down. It's an inherently wild and frenetic place. The laws in the quantum world are very different from the laws that we're used to. And is that surprising? Why should the world, of the very small and atomic level, why should that world obey the same kind of rules and laws that we're used to? In our world with apples and oranges and walking around on the street, behave the same way. The fluctuating, jittery picture of space and time, predicted by quantum mechanics, is in direct conflict with the smooth, orderly, geometric model of space and time described by general relativity. But we think that everything, from the frantic dance of subatomic particles to the majestic swirl of galaxies, should be explained by just one grand physical principle, one master equation. If we can find that equation, how the universe really works, and every time and place will at last be revealed. You see, what we need is a theory that can cope with the very tiny and the very massive, one that embraces both quantum mechanics and general relativity and never breaks down, ever. For physicists, finding a theory that unites general relativity and quantum mechanics is the holy grail, because that framework would give us a single mathematical theory that describes all the forces that rule our universe. General relativity describes the most familiar of those forces, gravity.